Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on Advanced Transition Metal Organometallic Chemistry. We have been discussing C-carbon heteroatom coupling reaction. In this context, in our previous lecture, we have looked at CN bond forming reaction, particularly with respect to amination of arene. Now, as had been mentioned in the last lecture, that carbon heteroatom bond forming reactions usually are formed by two approaches, and both of these approach require diasteric conditions, and both of this approach also is challenging to perform. And these two approaches had been nucleophilic aromatic substitution reaction, which requires diasteric conditions, as well as nucleophile addition to unsaturated alkenes and alkynes, which also is very challenging in absence of any catalyst. Now, today in that pretext we had spoken about palladium mediated CN bond forming reaction, and that how that helped in carrying out all these amination of aryl reaction under conditions which are more mild and not that drastic, and also more applicable in terms of the breadth and the depth of the chemistry is concerned. We have looked into aryl amination reaction in details, not only from the mechanistic point of view, but also its broad spectrum of applicability in the previous lecture. Today, we are going to take another example from the second approach that we had just mentioned about, that being addition reactions to alkenes and alkynes. And in that context, we are going to be talking about this hydroamination reaction. Hydroamination reactions is nothing but addition of ammonia or primary or secondary amines to alkyne and alkynes, addition of ammonia, primary and secondary amines to alkenes or alkynes, yielding amines. Now, this reaction has significant interest. Not only it arises academic interest, but also it arises industrial interest, and this is primarily because of the fact that this reaction is an approach that is atom economic, that the reaction is atom economic. Which means that there is no side products produced, and this so this is the atom economic approach to formation of amines, and that is why this is of industrial importance, that they would really love to have a method in which they can make amines without producing any byproduct or any waste material in the process of making this amine, and hence the atom economic reaction helps in the cause. The other challenge, as I said, is also very academic in nature, in the sense that these amines and olefins or alkynes, all the reacting substrates are all of them are very electron rich entities, and hence they are averse to mutually react, and as a result this hydroamination reaction indeed is very challenging. However, the landscape changes as one moves from non-catalytic to catalytic reactions using transition metals. Then the metal catalyzed hydroamination reactions, however, are feasible and can also be performed in a mild conditions, and that is why transition metal catalyzed hydroamination reactions have been pursued vigorously with the intent of developing preparative methods for producing amines, which are not only convenient, but also environmentally benign, in the sense that there is no waste material produced in the large scale synthesis of these amine reagents. So, in general, so drawback has been that these hydroamination requires drastic conditions in absence of the catalyst. However, the advantage is, if one can be made to do so, that this reaction is atom economic, as well as these amines and alkenes or alkynes are considered electron rich, and hence they are mutually averse to react, and hence normally, as I said, that hydroamination reaction requires drastic conditions, or there are catalysts which are limited applicability and high cost. So, in this context, BCP titanium dimethyl is an excellent catalyst for inter and intramolecular hydroamination of alkynes. BCP titanium dimethyl is an excellent catalyst for the inter and intramolecular hydroamination of alkynes, and this is illustrated in the equations below. For example, the alkyne R1 R2 plus R3 NH2 in presence of catalyst Cp2 titanium dimethyl toluene 80 to 100 degrees centigrade provides this hydroaminated product R1 R2 and R3, which under further conversion gives amines, ketones, amino acid, etc. So, here one can see that this is the case of intermolecular hydroamination, where NH is adding against the double bond to form this imine compound that can finally be converted to amine by reduction or hydrolysis ketone or amino acid, so on and so forth. So, there are not only the example of intermolecular hydroamination, there are well known examples of intramolecular hydroamination. So, the example of intramolecular hydroamination using hydroamination using this same BCP titanium dimethyl catalyst is given over here. R1 N H2, catalyst Cp2 titanium dimethyl, giving N R. So, this is this NH adding across this alkyne in an intramolecular fashion, which again can be converted to amines, ketones, amino acid, and etc. So, what it shows that these hydroamination, when catalyzed using a transition metal, can be used to convert in a very effective manner to various amines, amino acids, ketones, and other useful reagents. So, having seen the utility of catalyst in bringing about the activation barrier, or bringing or making the hydroamination reaction facile to be practiced within the laboratory conditions. Now, we are going to be interested in looking at the catalytic cycle for this particular hydroamination reaction. So, the active species for this hydroamination reaction for this titanium bis-cyclopentadienyl titanium dimethyl is a titanium imido species, and that is generated by reaction of titanium bis-Cp titanium dimethyl with this amine. So, this is the catalytic cycle is best illustrated in the following example, when this bis-Cp titanium Cp2 titanium dimethyl, when reacting with R3 2 of R3NH2, which this NH and methyl will eliminate methane to give this compound Cp2 titanium in HR3 whole 2, that will eliminate one molecule of R3NH2 to give the active species, which is bis-Cp2 titanium in R3. This is a imido species. Now, this imido species undergoes reaction with the acetylene R1 R2 in a 2+2 cycloaddition to give the product Cp2 titanium in R3 olefin R1 R2. So, this addition happens in a 2+2 cycloaddition fashion. To give this cyclic 4-membered metallocyclobutane kind of species. So, this intermediate is popularly called as aza-titanocyclobutene, aza-titana cyclobutene, CYCLO-butene. So, this is aza-titanocyclobutene. So, this species then reacts with another molecule of the amine, R3 NH2, to give this amine attacks, and then this cyclobutene ring opens up to give Cp2 titanium in R3 R2 double bond R1 NHR3. So, what really happens is that one of the proton then cleaves this titanium carbon bond upon coordination of amine over here, and then this carbon gets protonated with the amine proton, giving this CH over here and the nitrogen. So, this ring just opens up from this titanium carbon bond, and this process is called aminolysis. This elementary reaction is thus called aminolysis. Subsequently, elimination from these titanium amidoamine species, which is a simple elimination, enamine elimination step, in which enamine is eliminated to give R1 R2 NHR3 that is in equilibrium with R1 R2 NR3, giving the imine product. So, here we see is that a very nice catalytic cycle, and one interesting thing about hydroamination reaction is that the catalytic cycle consists of 3 elementary steps. The first one is this 2 plus 2 cycloaddition, followed by aminolysis in presence of excess amine, and third is amination elimination reaction, eliminating enamine as the product and regenerating back the titanium imido species. So, this catalytic cycle is by far different from the other catalytic cycles which we had been discussing so far, in which there were 4 elementary steps, and 2 of them were oxidative addition, reductive elimination, the other 2 coordination insertion or coordination deprotonation, so on and so forth. So, here we see that this hydroamination reaction indeed proceed by a different catalytic mechanism, in which it involves 3 elementary steps, and catalyst does plays a important role in carrying out this challenging catalysis. Now, the scope of this reaction was subsequently extended in performing this reaction under asymmetric condition. Now, one can sort of gauge the utility or advantage of using hydroamination reaction under catalytic condition by comparing it with the fact that typical addition of ammonia to ethanol happens only at 190 degrees centigrade at 900 pressure. So, it is that difficult reaction. Typical typical addition of ammonia to ethylene only happen at 190 degree centigrade, 900 bar pressure. So, this says that how much a drastic a condition is required just to add ammonia to ethylene in absence of the catalyst, whereas intermolecular hydroamination catalysis occur at mild condition. Now, as mentioned that the scope of the reaction has been extended to carrying it out in under asymmetric conditions, and asymmetric hydroamination reaction has been achieved at ambient conditions, that is at room temperature using Nairi catalyst. Was achieved using Nairi catalyst at 45 degree centigrade, mild temperature, and this is beautifully illustrated by the reaction discussed over here. Plus amine giving R binap PD O SO2 CF3 in toluene 45 degree centigrade, giving this hydroamination product CF3 NH pH in high yield 81% yield and high EE 81% in enantiomeric excess. So, this is indeed a breakthrough in which this hydroamination reaction has been performed in an enantioselective fashion, and that too at very mild condition of 45 degree centigrade. And with this I would like to conclude today's discussion on hydroamination reaction, and before we move on to other kind of carbon heteroatom bond forming reaction. Now, to summarize, what we had seen is we had seen the challenges that are often associated with hydroamination reaction, and that is because of the fact that both the amines and the olefins or the alkynes are extremely electron rich entities which are mutually averse to reacting to each other, and this can be typically gauged from the fact that the addition of ammonia to ethylene can only occur at a very high temperature of 190 degrees centigrade and at a pressure of about 900 bars. So, which sort of explains that how difficult it is for these amines and electron rich entities like amines and alkenes or alkynes to react. Now, given the scenario, there are a lot of advantages to come out of this approach, in the sense that if it does react, this reaction is completely atomiconomic without the production of any kind of byproduct waste materials, and as a result this approach is quite important from industrial point of view. Now, this hydroamination of alkene and alkyne is indeed a problem which is of both academic as well as industrial interest. Now, this has been cleverly solved using a nice demonstration of the concept of catalysis using transition metal complexes, how the catalytic reactions overcome the inherent difficulty associated with the mutually reacting substrates. And this has been clearly observed in case of a titanium hydroamination catalyst, which is of the formulation bis-cyclopentadienyl titanium dimethyl, which can carry out both intermolecular as well as intramolecular hydroamination of alkynes to give the corresponding imines, and that can be finally converted to amines or ketones or amino acid, depending on the conversion one takes resort to. We have also taken a look at the catalytic cycle for this hydroamination reaction as mediated by bis-cyclopentadienyl titanium dimethyl precatalyst, and what we had seen that the bis-cyclopentadienyl titanium dimethyl precatalyst initially reacts with two equivalents of amine to give the bis amido titanium complex, which loses one amine to make the titanium imido complex, which is the active species that initiates the catalytic cycle. In particular, in the catalytic cycle, the alkyne reacts with the titanium imido species in a 2+2 cycle addition to give an aza-titana cyclobutene macrocycle which then undergoes aminolysis using the large excess of amines that are present to give a titanium amino imido species that undergoes elimination to give N-amine, which finally rearranges to give the imine. So, this is a nice demonstration of catalytic cycle. Also worth noting, as we have discussed while during the catalytic cycle, that this hydroamination catalytic cycle consists of three steps. The first one obviously is the 2+2 cycloaddition, second one is aminolysis, and third one is the elimination step, and this is quite different from the other catalytic cycles for CC or CN coupling reactions that we have spoken about, which consisted of 4 catalytic cycles and 2 of which obviously involved reductive elimination and oxidative addition. We have also seen that the scope of the hydroamination reaction can be extended to be able to carry out asymmetric hydroamination under mild condition at a temperature as low as 45 degree centigrades, producing the desired enantioselective products in high yield and higher enantiomeric excess. So, with this I would like to conclude our today's discussion on hydroamination reaction, and we are going to be looking at other kind of carbon heteroatom coupling, and we are going to move on from CN coupling that we have been discussing in the form of amination of arenes and hydroaminations to another famed B coupling, which is hydroboration reactions. This also is an addition reaction similar to the hydroamination reactions that we have been discussing so far. So, with that, I again thank you for patiently listening to me in this lecture, and I look forward to take up this topic on hydroboration reaction in bit more in quite detail as we meet next time. Till then, goodbye and thank you.